Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there.
Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the AQA A-Level Chemistry paper from June 2017. This question is about silver iodide. Define the term enthalpy of lattice formation. So the enthalpy of lattice formation is the enthalpy change when 1 mole of a solid ionic lattice forms from its gaseous ions. Some enthalpy change data is shown in Table 1. Use the data in Table 1 to calculate the enthalpy of lattice formation of silver iodide. So if you've seen my other videos on any enthalpy change question in the universe, you're going to say the same thing. You cannot do this without doing a cycle. You can't jump in using some weird formula. There's literally no other way around doing this. If I catch any of you doing it, I'm going to, I don't know, do a cartwheel off a cliff into a wooden box, and then I'm going to put the wooden box in a wood chipper, and then jump out the wooden box, being wood chipped right before I die, because I don't want to die just yet. And then, yeah, just don't do it. The strategy is to always write out an overall equation first, and remember that every single arrow in a Hess's law cycle is an enthalpy change. So if it's the enthalpy of lattice formation of silver iodide, then you're going to be making 1 mole of a solid ionic compound, in this case silver iodide. I'm going to write the lattice enthalpy here. And then it's going to be Ag plus gas plus I minus gas. You should be able to know each enthalpy change and how to write it as a formula. Then what you do is you look at the table and see what they've given you. So this is an enthalpy change where it's a solid to aqueous. That's the enthalpy of solution. This is gaseous ion to aqueous ion, so that's enthalpy of hydration. This is gaseous ion to aqueous ion, so that's enthalpy of hydration. Then what you do is you compare all of these to what you have in the question. We have gaseous ions, we have a solid ionic lattice. And if I see I have a solid ionic lattice here, and it becomes aqueous, and I have gaseous ions, and they become aqueous. So I could put at the bottom of this cycle is this Ag plus aqueous plus I minus aqueous. Then what you do is you look at all of them one by one and draw arrows. Don't immediately try and draw arrows without comparing. Every enthalpy change, remember, is an arrow. So if we go from gaseous to aqueous, that's what they've given us in the question, we put an arrow this way. And then here, same thing, this way. And then solid ionic lattice to aqueous ions, so it's this way. Then you put the numbers in, so it's going to be minus 464, minus 293, and then 112. So then you can find it because you know that if you start from here and here, the enthalpy change will always be the same no matter what route you take, even if you go down this way instead. Therefore, the lattice enthalpy will equal this arrow going down to minus 464, this arrow going down, minus 293, and then from here we're going up, so it's going to be the opposite of this, so that's plus 112 down, so that's going to be minus 112 up. If we do that, we get minus 869 kilojoules per mole. A calculation of the enthalpy of lattice formation of silver iodide based on a perfect ionic model gives a smaller numerical value than the value calculated in question 1.2. Explain this difference. So a perfectly ionic model or a purely ionic model assumes that these ions are spherical and unpolarized, meaning that their charge is evenly distributed across both of them. Whereas when you have partial covalent bonding, what happens is the electrons in this negative ion are actually dragged towards the positive ion like that. It's pulled towards it. The reason is because those positive ions are now polarizing the neighboring negative ions, right? What you find is that experimentally, they actually tend to be more exothermic, as in more negative versus in theory. If that's the case, then that means more. Remember that exothermic is energy released, which is bond making. So if this has released more energy when there's bond making, you could almost think of it as there's more bonds made. And I don't know if that's like technically correct per se, but this is how it makes sense to me. Because if you've got more bond making, that means you must have covalent character as well as the ionic bond. In another way, I guess, this isn't maybe not technically true, but it helps me remember, right? Is that when you've got covalent character, it's like you've got ionic bonding plus covalent on top of it, which gives you a more exothermic enthalpy change because there's more, bonds made. So here, a calculation of the enthalpy of lattice formation about silver iodide based on a perfect ionic model gives a smaller numerical value. Explain this difference. It's because it must have a covalent character. So AGI has covalent character because the forces holding the lattice together are stronger. Because if you've got more of those bonds being made, again, not technically correct, I think, I don't know, but it just helps me make sense of it. Definitely the bonds are stronger, but like I like to think of it as more energy is released, more bonds have been made. So identify a reagent that we can use to indicate the presence of iodide ions in an aqueous solution and describe the observation made. So it's something that you're adding to this directly to get an immediate thing out of it. So what you're going to add is you are going to add AgNO3 and you get a yellow precipitate. There you go. This question is about acidic buffers. The acid dissociation constant K of ethanoic acid is given by this expression where the value of K is this at this temperature. A buffer solution of this pH was prepared using ethanoic acid and sodium ethanoate. In the buffer solution, the concentration of ethanoate ions was this. Calculate the concentration of the ethanoic acid in the buffer solution and give your answer to 3 significant figures. So what they're trying to get you to find, if I just rewrite this in terms of H plus and A minus, so we'll do it, follow their ones. It's going to be A minus, H plus over HA. Right? Always figure out what you've got first, and that makes a lot more sense. We have Ka, which is 1.74 times 10 to the minus 5. We have the pH, which is 3.87. Therefore, we could say that H plus, the concentration of it, is going to be 10 to the minus 3.87. And they've told you, in the buffer, the concentration of ethanoate is this. So we know that our A minus now is going to be 0.136. The question wants you to find the concentration of acid, which is HA. So then all you do is you just rearrange the Ka formula to find what HA is. So then in that case, Ka equals H plus A minus over HA. So then HA would equal, if you times that by that, you get Ka times HA equals these two, and then divide by Ka. So it's going to be A minus H plus over Ka. So that means HA is going to equal A minus, which is 0.136 times 10 to the minus 3.87 for the H plus, all over 1.74 times 10 to the minus, 5? Yep. If we do that, we get 1.054, roughly 1.05 moles per deciliter cubed. There you go. In a different buffer solution, the concentration of ethanoic acid was this, and the concentration of ethanoate ions is that. A 7 times 10 to the minus 3 mole sample of sodium hydroxide was added to 500 centimeters cubed of this buffer solution. Calculate the pH after the sodium hydroxide was added and give your answer to 2 decimal places. So a lot of people I see just jump straight into doing like I already know the H plus A minus blah 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 blah, and fumble it horrendously. Buffers are equilibria. They work by shifting equilibria. So in this case, just like the other questions in equilibria where it's like a scientist makes this and that, blah, 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 and equilibrium equals this, it's the same thing. So what you need to do is you've got to write out an equilibrium first. So what I always like to do is I like to just write the basic acid-base equation. So what I mean is that an acid plus a base makes a salt plus water, and then I'll label it. So an acid is always HA in this context, a base is always OH minus, a salt is A minus, and the water, we don't care about is H2O, but it doesn't appear in any of your Ks and this and that's right, unless it's KWs. So here then, what you do is you need to first of all do moles before reaction, your moles after reaction, and then whatever you need here. So we're going to need concentration eventually if we're going to do Ka. So now we need to think about this before the reaction and after. So we know what. This is where it requires you to read the question and use some reading comprehension skills. So in a different buffer solution, the concentration of ethanoic acid was this, right? And they've added it to this sample here. So before our reaction, before we've actually, when everything's first mixed together is what this is, right? You're going to have how many moles of acid? We're going to have 0.260 times 500 over 1,000. If we do that, we get 0.130 moles of acid. Cool. The moles of base that they've just added, we're working only on just what they just about started, is going to be 7 times 10 to the minus 3 moles, as per the question, right? Now, how much salt did we have before this reaction actually started taking place? Again, it's just when everything's mixed. It's told you that the concentration of ethanoate ions, which is A minus, which would have come from the salt, is this. So then you would have 0.121 times 500 over 1,000. If you do that, you get 0.0605, and water we don't really care about because it doesn't come up in the Ka equation. Now, we need to think about what's going to happen to this as we've added the base. Think about it with some common sense. Your equation says acid plus a base makes a salt and water. If you've just added base here, this base is going to react with that acid, and they're both going to decrease in number. So this is a lot smaller than this. So what happens is, after the reaction, you end up with none of this left because all of it's reacted with this. So you get that, 0. If that's gone down by 7 times 10 to the minus 3, this will have also decreased by 7 times 10 to the minus 3 because one of these reacts with one of those. If that's the case, then the amount of acid after all of the stuff's happened is going to be 0.123 moles. Base, we have none left because it's all reacted. Now, one of these ends up making 1 mole of salt. So if that's gone down by 7 times 10 to the minus 3, this will have gone up by plus 7 times 10 to the minus 3. If we do that, now the moles of the A minus after is going to be 0.0675 moles. Water don't really care about. Now we need the concentrations of all of these. Now, although it doesn't say the volume's changed outright, it doesn't say anything about assuming that the volume stayed constant, so I'm going to say that presume the volume has changed. So whatever this concentration is going to be is 0.123 divided by its new volume. I'm going to rewrite that as 1 over V times 0.123, just because it looks easier to work with. Here, the new concentration is going to be 0.0675 as well, divided by the volume, which is then going to be 1 over V, 0.0675. Now that's remember, concentration of HA is the concentration of A minus. The question wants us to find pH, so we want to find H plus, and we know that Ka is from here because it's ethanoic acid. Ka equals H plus A minus over HA. So Ka times HA over A minus equals H plus. So if that's the case, H plus will equal 1.74 times 10 to the minus 5, the Ka, times our A minus, which is 1 over V, 0.0675, all divided by the HA, which is 1 over V, 0.123. Now you're timesing these two together, and you've got 1 over V in here and here, so this cancel out actually. So then you end up with a nice thing of this times this divided by this. If we do that, we get 3.1707 times 10 to the minus 5, and that's your H plus. And if you do pH, it's negative log to the base 10 of your answer. You get 4.498, which is roughly 4.5. You got to do it to 2 decimal places. There you go. What is the correct expression for Kw? It's C. It's just C because the water concentration is effectively the same, so that's just cancelled out. Now it says calculate the pH of pure water at 10 degrees Celsius and then give your answer to 2 decimal places. So Kw is going to equal, in pure water, H plus and OH minus are the same. So it's roughly equal to H plus squared. So that means H plus is going to be the square root of Kw, which is whatever they've given us in the question. So here they've told you it's 2.93 times 10 to the minus 15. 2.93 times 10 to the minus 15, which is going to be square root of that, which is going to give us 5.41 times 10 to the minus 8. And then pH is going to be negative log to base 10 of this, which is 7.2666, which is roughly 7.27. There you go. 2 decimal places. So just why this pure water is not alkaline, the reason is nothing to do with the number of the pH. This pH only just measures how many H pluses there are. It is that H plus is equal to OH minus. That's why it's not alkaline. Now it says calculate the pH of a 0.0131 mole decimeter cubed calcium hydroxide solution in this and give your answer to 2 decimal places. So you need to think in here what's going on, what we're dealing with. We're dealing with an alkaline solution, a base, and that's going to be CaOH2, which if you dissociate that, it becomes Ca2 plus and 2OH minus, right? They've given you this mole per decimeter cubed, all right, and it's a strong base. So if this is 0.0131 as a concentration, mole decimeter cubed, every single one of these puts out 2 of them. So the concentration of this is going to be 2 times that. So it's going to be 0.0262 moles per decimeter cubed, right? Kw is the only one of these that link H plus and OH minus. So that means H plus is going to equal Kw divided by the OH minus, which if we look, it's at the same temperature as the one before, so it's going to be the same Kw from before, so 2.93 times 10 to the minus 15. So 2.93 times 10 to the minus 15 divided by this OH we've just worked out, because there's 2 of them for every one of these, which is 0.0262. If we do that, we get 1.1183 times 10 to the minus 13, so then pH is going to be negative log to base 10 of your answer. And if you do that, you get 12.95. Done. The 0.0131 mole per decimeter cubed calcium hydroxide solution is saturated. A student adds this much magnesium hydroxide to this much water and stirred until no more solid dissolved. Predict whether the pH of magnesium hydroxide would be larger than, smaller than, or the same as the pH of calcium hydroxide, and explain your answer. So if we have a look, we need to compare them fundamentally to what their differences are. The only difference between these two is that magnesium is up here and calcium's one down, so it's got an extra shell in it. So we need to think about what possible things could change about them. We're dealing with group 2, so as you go down with group 2, what happens is it becomes more soluble, the OH minus. Whereas as you go down for the other one, it becomes SO42 minus is less soluble, right? It's the opposite. So if you go, the way to remember is that barium sulfate is insoluble, and that's like really low down compared to the others, right? So here, if this is less soluble, there's going to be fewer OH minuses out there, like being put out. Now you can prove it mathematically as well, because if H plus is Kw divided by OH, if you have fewer of these, then this thing's going to go up. If that's going to go up, there's more H pluses, meaning it's more acidic. If it's more acidic, it means the pH is going to be lower. So there you go. The explanation is that MgOH2 is less soluble, so there's less OH minus, therefore more H plus, therefore more acidic. There you go. A sample of titanium was ionized by electron impact in a time of flat mass spectrometer, and here's the information. It says, but work out the relative atomic mass. So relative atomic mass is just going to be each one of these times, each other, and then divided by the total you have. So it's going to be 9.1 times 46 plus 7.8 times 47 plus 74.6 times 48 plus 8.5 times 49. And if I just double check, all of these add up to 100. So you divide it by 100. So then all you do is you just type that into your calculator and plug in. So if we do that, we get 47.8. Now it says write an equation including state symbols to show how an atom of titanium is ionized by electron impact and give the MZ value of the ion that would reach the detector first. So when you're doing electron impact, you're knocking off an electron from this. So we've got titanium and it's going to be gaseous. And then what you end up with is it's lost an electron. And so it's going to be Ti plus gaseous. There you go. It says, and then give the MZ value of the one that would reach the detector first. The one that reaches the detector first is the one that moves fastest, which is going to be the smallest one. So the smallest one here is 46, so its MZ value is going to be 46. There you go. Now it says calculate the mass in kilograms of one atom of 49 Ti. So this number here, 49, means it's grams per mole. Every single mass in your periodic table is in grams per mole, meaning that 1 mole of whatever it is will weigh this many grams, right? So if 1 mole weighs 49 grams, right, 2 moles would weigh, 2 times 49 grams. Pretty straightforward, right? 1 mole of them is Avogadro's constant. If I have 1 mole of bananas, I've got 6.02 times 10 to the 23 bananas. So technically speaking, this is actually instead 6.02 times 10 to the 23 atoms weighs 49 grams. So if we want 1 atom, you divide it by 6.02 times 10 to the 23. So it's going to be 49 divided by Avogadro's constant. But they also want this in kilograms. So we're going to convert that to kilograms by dividing by 1,000 as well. If you do that, you get 8.1 times 10 to the minus 26. There you go. So if, for example, carbon 12, the reason it weighs 12 grams is because 1 mole of carbon weighs 12 grams. There you go. And 1 mole, again, is Avogadro's constant. If I have 1 mole of bananas, I have 6.022 times 10 to the 23 bananas. In a time of flight mass spectrometer, the time of flight T of the ion is shown by this equation. In this equation, T is the length of the flight tube, M is the mass of the kilogram of an ion, and E is the kinetic energy. In this spectrometer, the kinetic energy is this. In the time of flight of this ion is this. Calculate the time of flight with 47 ion and give your answer to 2 significant figures. So there's multiple ways of going around this, but what I'm just going to do is I'm going to just look at what we know so far. So for this 49, we know that this is going to be, 9.816 times 10 to the minus 7. Cool. They're all going to be given the same kinetic energy. So the only thing that's changing, the length is the same, the energy is the same. The only thing that's changing is the mass. So that means that the time is proportional to whatever's changing. So it's going to be square root of m, right? So if 49 gave us 9.816 times 10 to the minus 7, right? Then we're going to 47. 47 gives us what? Now, remember that this is like the square root of 49. This is square root of 47. So if we're going to go down to this, then what we're doing is we're really dividing it by the square root of 49 and then timesing it by the square root of 47, right? So in this case, we're going to do the same thing here. We're going to divide it by the square root of 49 and we're going to times it by the square root of 47. If we do that, we end up getting 9.6135 times 10 to the minus 7 seconds, or roughly 9.614 seconds. There you go. Because the only thing that's changing between the two of these is its mass. So whenever you're doing that, you can literally compare it like that. In the same way here in this previous question, I said 1 mole weighs this, so 2 moles must be 2 times this. Here, root 49 gave us this, so then root 47, if I were to do like 2 root 49, it would be 2 times that, right? So if I'm going down to from root 49 to 47, I'm dividing it by root 49, that gives us 1, and then I times it by 47, that gives us, root 47, and then it would do the rest. That's the way I'd do it, to be honest. So titanium chloride can be made by titanium oxide as shown in this equation. Some entropy data is shown. We'll calculate the Gibbs free energy and then give your answer to appropriate number of significant figures and then say whether it's feasible. So delta G equals delta H minus T delta S. So we have delta H, which is going to be minus 60. We know that the T is going to be 989 Celsius. So to convert it to Kelvin, we need to add 273. So 989 plus 273 gives us 1262 Kelvin. We do not have delta S. Delta S is going to be S end minus S start. Generally speaking, any change in something is always the end minus the start, right? So then it's going to be the entropy at the end minus the start. So it's going to be delta S is going to equal the entropies of, so 2 lots of CO, which is 198, plus 1 lot of TiCl4 plus 253, minus the start stuff. So TiO2, this is one of them, so 50.2, minus another, actually we could do minuses for all of them, that's probably easier. 2 lots of 5.70 minus chlorine, minus 2 lots of 223. If I do that, I get delta S to equal plus 141.4 joules per Kelvin per mole. Now the problem is that these formulae do not work unless everything is consistent. Now if that's in joules per Kelvin per mole, I need to convert joules to kilojoules. So it's going to be 0.1414 kilojoules per Kelvin per mole. Now I can slap this into delta G, which will be delta G equals delta H minus 60 minus T, so 1262 times delta S, which is 0.1414. If I do that, we get minus 238 kilojoules per mole. So that's the answer, but then the explanation is that this delta G is less than 0, therefore the reaction is feasible. There you go. So it says write an equation for the reaction of phosphorus with an excess of oxygen. This is a specific example you need to know. So it's going to be P plus some amount of O2. P4, sorry, makes it plus O2, gives you P4 O10. Balancing it, it's 5. You can't have P2O5. This is an example they specifically want. Now it says, describe a test you could carry out in a test tube to distinguish between sodium oxide and the product of the reaction in this here. So if we're having a look, we're going to test it between sodium oxide and that. Now, what I can do is I can react them with water, because this is sodium oxide. If I react with water, I'm going to get sodium hydroxide. And if I react this with water, I'm starting to get phosphoric acid. That's what I'll do. So first of all, I'll add water. The sodium oxide becomes sodium hydroxide. This P4O10 becomes phosphoric acid. But we're not done yet. We need to actually test it. So what I'm going to do is I'm just going to add, like, I don't know, universal indicator. And for this one, I'm going to call it 1 and 2 because I'm lazy. You write the whole thing, obviously. For sodium oxide, it would go, like 12 to 14. It'd go like blue. And then for 2, it's going to be much more acidic, strongly acidic. So it's going to be like 2-ish, like 1 to 2. And it's going to be like, red. Alternatively, you could talk about using litmus paper, or you could use a pH meter as well, I guess. State the type of crystal structure shown in silicon dioxide and sulfur trioxide. So silicon dioxide is a macromolecule or giant covalent, and sulfur trioxide is just a simple molecule. The key examples of giant covalent are diamond, graphite, graphene, and silicon dioxide. Now it says, explain why silicon dioxide has a higher melting point than sulfur trioxide. When you're melting something, you're putting energy in to break bonds between stuff. Now here, what we need to think, in a giant covalent compound, what are you actually breaking? A giant covalent is everything bonded together covalently. Like, everything is held together with, that's when the only time when you're actually breaking the covalent bonds. Whereas sulfur trioxide, imagine there's one sulfur trioxide, there's another. You're breaking the bonds between these molecules, not the actual ones within them, otherwise you would just end up with sulfur and oxygen atoms, which is incorrect. So then we need to explain what the difference is here and what we're actually breaking. So here we're breaking covalent bonds, but sulfur trioxide, we're just going to be breaking van der Waals forces and dipole-dipole forces. There's no hydrogen bonds or anything like that here. So it says in the question as well that silicon dioxide has a higher melting point. So it must be that the bonds we're breaking here, the covalent bonds, are stronger than the ones we're breaking here, which are the van der Waals forces. So that's exactly what you're going to say. So SiO2 has covalent bonds between atoms. Well, between atoms, they require more energy to overcome and are stronger than the weaker van der Waals and dipole-dipole intermolecular forces. Intermolecular forces. Intermolecular means between molecules. Between molecular molecules. Forces in sulfur trioxide, which require less energy to overcome. There you go. Now it says write an equation for the reaction of sulfur trioxide with potassium hydroxide. So just write what you know straight away. So you're now going to react SO3 and we're going to add KOH. So we need to figure out what we can make. Most likely, what I'm looking at is that I'm seeing KOH plus an SO3, which can act as an acid. So we're probably going to make K2SO4, right? So this can be acidic, but acts as a base. And if we're going to add that together, we're going to make water. So H2O here. And I'm going to balance this out because there's K2 now. So there's 2 KOHs there, and that's it. Write an equation for the reaction of an excess of magnesium oxide with phosphoric acid. So again, start with what you know. So MgO plus H3PO4, what are we going to make? So it's a metal oxide plus an acid. That's going to make a salt plus water. So at least I know on this side I'm going to make water. The salt's going to be, well, that's 2 plus, and one of these PO4s are 3 minuses. So we're going to have Mg3PO4 2. So now we need to balance that out because there's 2 PO4s, there's only 1 here, so 2 there, and then we need 3 Mgs, so there's going to be 3 here. And then how many waters do we need? So we've got 2 H3PO4, so it's 6 H's, and there's the only thing that has H on this side is here, and there's 2, so that's got to be 3 there, because that'll give you 6 and it balances it out. Done. Now it says, draw the displayed formula of the undissociated acid when sulfur dioxide reacts with water. If you've got sulfur dioxide, SO2, and we're adding water, then we're going to make H2SO3, so you've got to draw that. So we're going to have an S, which is in group 6, so it's going to have 1, 2, 3, 4, 5, 6, right? Outermost electrons. Now it's H2SO3. We need to put 3 oxygens on here, 2 of which are going to be OHs on them. So if there's an OH here, then there's probably going to be an O here and an H like this, because O wants 2 extra, bonds, covalent bonds to fill in its outer shell. Here, it's going to be O and H as well. So we've dealt with 2 of the O's. We've only got 1 O left. We need to figure out where to put it. So 1, 2, 3, 4, 5, 6. We have 1 O left. So the O, the other one's probably going to make a double bond here, because the O, remember, wants 2 bonds. And there you go. We have a lone pair of electrons, got our oxygen here, and that's it done. Solution A contains this compound CuH2O6Cl2 and says state the type of bonding between the oxygen and hydrogen. A lot of people just misread this and went straight for dative covalent or coordinate. It's between the oxygen and hydrogen, which is an H2O, so it's actually just straight up just normal covalent. There you go. State why the chloride ions are not considered to be ligands, because it's not within this complex ion here, right? It's outside here, so that means there's something going on that's stopping it from being a ligand. What makes a ligand is it donating electrons to the central metal ion, as in forming a coordinate bond. Here, if it's not a ligand, it's not forming a coordinate bond. So no coordinate bond formed. But you need to say why. Because it's not donating an electron, I should really say lone pair to the Cu2+. A ligand can only be a ligand if it's got a lone pair of electrons to give. An excess of ammonia was added to a sample of A to form solution B. White ionic equation for this when solution A is converted into solution B and the color of solution B. So start off with what you know immediately. So we know that solution A has this in it, right? Which is CuH2O6Cl2. This is going to dissociate into this thing, 2 plus, and then 2 Cl minuses, because that's an ionic compound. That's the same as just saying CuCl2, right? So that's the case, then we know we're definitely starting with CuH2O6 2 plus. Right, now the question's saying we're adding an excess of ammonia, whatever, fine, NH3, and we're making a solution. So if it's a solution, we're not going to be making a Cu like OH2H2O4 because that's solid. It's generally speaking, in this topic, if it's still charged, it's going to be a solution. So in this case, we're making something that still is a solution and is charged. And the only one that we should know, because it's an example you guys need to know, is CuNH3, 4, H2O2, 2 plus, a partial ligand substitution reaction. So in this case, now compare side by side. We have H2O6, H2O2, 4 H2O has been booted off, and we've stuck 4 NH3s on. So we're going to have 4 there. There you go. And the color it goes from is pale blue to dark blue. There you go. Aqueous sodium carbonate was added to another sample of solution A to form a blue-green solid C. Identify the blue-green solid C. So sodium carbonate, we're adding it to A, remember? A is CuH2O6 2 plus. Now this is under a subtopic called metal aqua ions, which is where a metal is bonded to water to form complex ions, right? Now, when you have a 2 plus metal aqua ion and you're adding a carbonate, it will form MCO3. Whereas if you have a 3 plus one, what will happen is they'll end up making the metal OH3H2O3, if that's a 3 plus. This is a 2 plus, though, so it's going to do that. So in this case, what's happening is that you're going to make CuCO3. There you go. Reagent D was added to another sample of solution A to form a yellow-green solution. Identify what reagent D is and write an ionic equation that occurs when the yellow-green solution is formed from solution A. So in that case, we're looking at solution A, remember, which is Cu whatever H2O6 Cl2, but that Cl2 is ionically bonded to this, not datively covalent, not dative covalent bonded. So that means this is going to be a 2 plus Cu2 plus ion, which is this. We're making it go yellow-green. The one equation that you need to know is doing this is that you're making CuCl4 minus. So you have H2O 6 2 plus. And one of the ones you need to know is Cl minus, which is where this Cl minus is too big, so you can't fit 6 around there. So you end up with CuCl4 2 minus, right? Plus the other waters that were booted off, 6H2O. So that means we're going to have to add 4 Cls like that. This is the key equation you need to know. And the reagent is what you're going to put in it to do this. We need to add something that provides Cl minuses, so HCl. That's this one here. So it goes from blue to yellow, or yellow-green. So if you're going from blue to yellow-green, it's most likely going to be the Cl minus is adding. The way I like to make sense of it almost is that when you're changing ligands, you're changing the color because the energy gap between the d orbitals, remember, is different, right? If the energy gap's different, it's either higher or lower, it's going to change the color. So this depends on the metal ion you're using, the oxidation state, and the ligand on it, right? Now, the way I like to make sense of it, not technically true, is that because you can only fit 4 of these, you're having a much more drastic change than if you were to swap it for 6 NH3s, for example. So the energy gap changes more drastically, which is why you get yellow-green. For example, here, we've only swapped off 4 of them, so it's still darkish blue, but not as great. Whether that's true or not, I don't know, but it's just a way to make me make sense of it, because, again, it's much more drastic to have 4 Cl minuses here instead of, just 6 NH3s. Explain why colorimetry cannot be used to determine the concentration of solutions containing this, and you should refer to the electron configuration of the metal ion. So, here, we've got CuCl2 minus. If that's got a -2, then the oxidation state of Cu must be +1. They've told you cannot use measuring colors to figure out why. So we need to think about what possibly could be going on here. Now, this is in the topic of transition metals, and we've now got a different oxidation state of copper. So the best thing to do is look at its electron structure, and it's also telling you to do that. So I'm going to get the periodic table, one sec. So if you look at this periodic table, a really quick shortcut is that this is the S block. Remember, that's the D block. That's the P block, right? So a lot of people know that this is the case, but they don't actually know how to read it, which is really goofy to me. That's period 1, period 2, period 3, period 4, period 5, period 6, period 7. The period tells you the outermost shell number, right? So for example, if I pick chlorine, I know it's going to be 3. It's in the P block, so it's P something. And it's going to be P1, P2, P3, P4, P5. So I know that it's going to end with P3, P5. This works for everything except the D block is where it gets a bit weird. The reason is because in the D block, remember that 4s fills first? So that's why it's technically in period 4, even though they all end in 3D something, right? That's just something to keep in mind. But everything else is the same. So in this sense, scandium would be 3D1, 3D2, 3D3. This would be 3D4. However, chromium is one of the weird ones where it prefers to be, instead of 4s2, 3D4, it actually prefers to be 3D5 instead, so 4s1, 3D5 instead. So then if we carry on, 3D1, 3D2, 3D3, 3D5 instead, 3D5, 3D6, 3D7, 3D8, 3D9 is another one. Copper's the other weird one, and then 3D10. Copper's the other weird one because instead of being 4s2, 3D9, it actually prefers being 4s1, 3D10 instead. So in that case, here we're dealing with copper, which normally exists as 4s1, 3D10. If we've got a +1, we've lost 1 electron, but remember that the 4s fills and empties first. So if that's the case, Cu plus has got 4s 0, 3d10. Now, it's no longer a transition metal in this exact context, because a transition metal is something that can form a stable ion with an incomplete d subshell. Now, this is a stable ion without an incomplete d subshell. So copper itself is still a transition metal because it can still make ones with incomplete d subshells, but in this exact circumstance, it isn't. So if it's in a complete d subshell, there is no energy gap for the electrons to absorb and jump, excitation states and ground states and all that jazz. So it's colorless. So you would say exactly that. It's 3d10, it's a full d subshell, therefore it is colorless, as it cannot absorb wavelengths of light or frequencies, whichever one you want to call it. This question's about ion testing. Describe how a student can distinguish between aqueous solutions of potassium nitrate and potassium sulfate using one simple test tube reaction. If it's sulfate, you're going to add anything that's barium, chloride, nitrate, or hydroxide. Any one of those, because the reason is you are going to make, well, in KNO3, nothing happens, there's no change. Whereas in potassium sulfate, you're going to make barium sulfate, BaSO4's formed, so you get a white precipitate. That's the key test there for sulfates. You can add a barium whatever that isn't sulfate, obviously. Then it says, describe how a student can distinguish between aqueous solutions of magnesium chloride and aluminium chloride using one simple test tube reaction. So it has to be one easy peasy basic thing. I know that I could add NaOH, because this one's devious. So if I add NaOH to this NgCl2, right, it's going to be a white precipitate, because it's very, very insoluble. The question's told you it is with one simple thing here, and we're looking at aqueous solutions of these two, right? So I should really be saying excess sodium hydroxide, because if you add lots and lots of this, what will happen is it will form, and then precipitate, but then it will disappear because it can act as an acid. Aluminium hydroxide is amphoteric. So what happens is you get a white precipitate, which then disappears. There you go. What disappears when NaOH is in excess. There are several stages in the industrial production of methanol from methane, and the first stage involves a gaseous equilibrium between the reactions, methane and steam, and some gaseous products. Figures 1 and 2 show the percentage conversion of methane into the gaseous products under different conditions at equilibrium. So as the temperature, we're increasing it, and the percentage conversion seems to go higher and higher and higher, and then levels off about 100. Whereas if we increase the pressure, it seems to be that the conversion's decreasing. So it says, deduce the optimum conditions for the industrial conversion of methane and steam into gaseous products and explain your deductions. So immediately, let's talk about it step by step. So from the graphs then, we should see that, well, again, if you increase the temperature, the yield increases. That's what we've just said. So increasing temperature increases the yield, right? And then what else do we see? After a certain temperature, what is it? After 800-ish degrees, 820 degrees-ish, the yield stops increasing. It just kind of stays level. But then as well as that, the increasing pressure on this diagram seems to decrease yield as well. Fine. Now we need to think about we need to deduce the optimum conditions in the industrial thing and explain our deductions. So we've deduced that. Let's talk about the temperature thing then. So we need to figure out what the optimum temperature is. Now, the thing is here, our optimum temperature is going to be, did I say 820? It should really be 880, really. Oops. The optimum temperature is about 880 degrees because any higher doesn't increase the yield. You need to explain why that matters though. Because very high temperatures are expensive and require a lot of energy as well, right? Now here we need to talk about pressure. So the pressure As you can see, if we increase the pressure, the percentage conversion of methane seems to decrease, but it kind of levels off here. Really, the problem is we don't want to have too low of a pressure either, because any reaction in the universe requires two things: a collision in the right orientation, and for those particles to have a minimum amount of activation energy, no matter what. No reaction will happen unless those two both are met. You can have the activation energy, but two particles here, if they don't collide, then they're not going to react. So if you have a really low pressure, right, two particles shoved in this massive box, it's going to take ages for them to smack into each other. Whereas if we have this TD box with two of them there, they're going to collide. So we need to find a balancing act of a really good pressure so that we don't have too slow of a reaction, but we don't want to have too high of a pressure so the yield drops. So first of all, talk about that. Is that too low of a pressure means you'd have means lower rate, so the reaction would be too slow. No point in having the best yield ever if the reaction takes 20 years to do. So a compromise is needed. So then I would probably say a good temperature to use is probably pressure would be somewhere in between, right? So maybe like I don't know, like 2000-ish or something like that. Therefore, middle pressure of 2000, whatever unit this is, kPa, is a good balance, really. Because you don't want to have it so high that there's no yield, but you also don't want to have it so low as it takes ages. This equation shows the final stage in production of methanol, 20.1 moles of carbon monoxide, and this will place in a sealed container, and equilibrium is established at this temperature. The equilibrium mixture contains that much methanol. Calculate the amount of moles of carbon monoxide and hydrogen in the equilibrium mixture. So don't jump in just doing like, oh, it must be a 2-to-1 ratio, blah, blah, blah. Like, it don't work like that. What they've done is that they have, so before equilibrium, they mixed this much carbon monoxide, so 20.1, with this much hydrogen, 24.2. Before the equilibrium's even started, there is 0 of this, as nothing happened. At equilibrium, though, these will have reacted and gone down in numbers to make this. So the question's told you, when the equilibrium's established, you had this much methanol, so we had 2.16 methanols. So if we had 2.16 moles of methanols, that's gone up by 2.16. So these must have dropped to make this. So every one of these makes one of those, so that must have dropped by 2.16. But here, there's 2 of them, so 2 of these are needed to make one of them. So that must have dropped by 2 times 2.16. So that means that the moles of carbon monoxide at equilibrium has to be this minus this, which is going to be, what, 17.9, and then this minus this, which is 19.9. There you go, 17.9, 19.9. A different mixture of carbon monoxide and hydrogen is allowed to reach equilibrium. At equilibrium, the mixture contained this much carbon monoxide, this much hydrogen, and this much methanol. The total pressure was this. It says calculate the value for equilibrium constant at this reaction and then state its units. So the equilibrium constant for this would be Kp in this case, so CH3, so it would be, PCH3OH over the PCO plus, times the pH2 squared. Right, so we need to find the partial pressures of all of these. Partial pressure equals mole fraction times the total pressure. This is the worst acronym ever. PP, MF, and TP, man. Like, oh my. But anyways, we need to find the mole fractions of each of these and then eventually those things. So write everything out. So carbon monoxide, H2, and then the methanol, so the CH3OH. Right, so we know what about each one of these, and we can go by steps. So in carbon monoxide, we know we have 2.76 of this. We know that we have 4.51 moles of this. And we know that we have 0.630 moles of this. So the mole fraction is the moles over the total moles of whatever it is. So our total moles is going to be these all added up. So if we do that, we end up getting 7.63 moles. So mole fraction of this would be, so if I write like a little table almost, mole fraction, partial pressure. Mole fraction of this is going to be 2.76 divided by 7.63. This one's going to be 4.51 divided by 7.63. And then this is going to be 0.360 over 7.63, right? Then what I want to do is I want to work out the partial pressure, which is mole fraction times the total. So it's going to be this answer times the total pressure for all of them, basically. So if I do that, I end up getting, if I just make some space here, if I do that, we end up getting the partial pressures for all of these to be 228. This one's going to be 372, and this one's going to be 29.7. Cool, and then you just want to slap it into the Kp's equation. So Kp is going to equal the partial pressure of CH3OH, which is 29.7, divided by the CO, which is going to be 228, times the H2's one, which is 372 squared. If we do that, we end up with 9.41 times 10 to the minus 7. Done. But we're not done, because the question also wants units. So the pressures that we worked with are kilopascals. Kp is this. It's going to be kilopascals divided by something in kilopascals and kilopascals squared, so over kilopascals cubed. So you can say that's like almost like kilopascals to the 1. When you're dividing things, you subtract the indices. This is a 1 minus 3. So it's going to be kPa minus 2. There. Now here's this table that shows some half equations of their standard electrode potentials, and it says deduce the oxidation state of nitrogen in this and this. So if it's NO3, it's going to be minus 6. We need to make an overall of 1, so it's going to be plus 5 here. So there you go, plus 5. And then here it's minus 2, and it's 2. Something, well, this got to be 2 because it's got to be 0 overall. So it's plus 2. Now it says, what's the weakest reducing agent? So reducing agent, remember, reducing agent is what gets oxidized itself. It oxidizes itself and reduces something else. So we need to look for whatever here is the worst thing at getting oxidized, basically. So our options are here. So the E value, the more negative it is, the more you're going to be oxidizing. So in that case, the most positive is the worst self-oxidizer and other thing reducer, which is going to be this. So it's Cl. Well, we got to also go another step. You can't just say the whole thing. You need to say exactly what it is. You can't say Cl2 because here, the Cl2 is getting reduced. Remember that reducing agent is getting oxidized itself. So it's the thing that's worst at getting oxidized. It's actually this. It's the Cl minus because that's getting oxidized to go that way. So be careful. Don't just jump into writing the equation like that. Then it says, write the conventional representation of an E cell that has this EMF of this. So E cell, remember, is going to be E reduced minus E oxidized. They've told you that it's plus 0.43. So 0.43 equals whatever times something else, right? Sorry, minus something else. So we need to look at this table to find out what gives us that combination of this. Something has to be reduced and oxidized. So whatever's reduced minus something that's oxidized. So we look at all of them and just work out the possibilities. So it's going to be these two, because if you do this minus this, you end up getting plus 0.43. So if that's the case, then this one's going to be reduced, that one's going to be oxidized. So in the conventional representation, the one that's more negative goes on the left. So this one's going to be on your left, that one's going to be on your right. And we put the reduced forms on the outsides. So draw the half cells one by one first, and then the rest is quite all right. That's your salt bridge in the middle. So if we're going to put the more negative one on the left, it's going to be this, and the more reduced form goes on the outside. So we're going to have Cu solid, and then Cu2 plus aqueous on the inside, Cu2 plus aqueous. And then on this side, it's going to be the more positive one, which is here. So we're going to, remember, put the reduced form on the outside. So Fe2 plus aqueous and Fe3 plus. But the problem is, can you see how those are both aqueous? They're both in the same phase. So actually what you've got to do is you've got to have them with a comma separating them instead. So Fe2 plus aqueous, Fe3 plus aqueous. And we need some surface for them to actually do this reaction on, so you have to include a platinum electrode on the other end as well. Otherwise, it's not possible because it's just aqueous and aqueous. They're both just floating around. You need a surface for them to do all of that stuff to actually have the circuit running. So in that case, you've got to include that platinum electrode on the outside like that. Now it says, use this table to identify an acid that will oxidize copper, explain your choices of acid, and then use these data to suggest a possible equation and calculate the EMF of this overall equation. So there's multiple steps here. We want to oxidize copper. So we're going to look back at our table and choose whatever's going to oxidize copper. So this means we're oxidizing copper, it's got to go this way. So we need to have this one be our more negative. We need to choose an acid that has a more positive E cell, right? So if this is being oxidized, then whatever the acid is has to be reduced. So we need to pick an acid that is being reduced. So our options are here because that comes from H2SO4 and then this from HNO3. Now this one is more negative, so that wouldn't be oxidized, so that one's out. Our only choice is here because that's NO3 minus, which comes from HNO3, which dissociates into that. That's where the H pluses come from, and a bit of extra obviously as well. So if that's the case, that's being reduced. So then what you would say is exactly this. So you would say that the acid of choice would be HNO3. You can't just say NO3 minus. You have to, it's asking you what acid you would use. This is providing the HNO3s. HNO3, why? Because its E value is greater than the E value for the Cu2 plus, right? Which therefore means Cu solid is oxidized and then NO3 minus is reduced. Right? That's our first bit done. The next bit then is to use this data to suggest a possible equation for this reaction. So if this is being oxidized, it's going this way. If that one's being reduced, it's going that way. Now we have 2 electrons here. We've got 3 here, so we times that by 2, and we times that by 3, and then we combine them in those respective directions. Just for the sake of time, I'll just quickly do it. So it's 3 Cu solid plus 8H plus aqueous plus, remember just to cancel out things as well on both sides where they're appearing, but this goes to 3 Cu2 plus aqueous plus 2 and no, what's that? Aqueous plus 4H2O liquid. Then it says work out the EMF. EMF equals E reduced minus C oxidized, which is going to be 0.96 minus 0.34, which is 0.62 volts plus 0.62. You should really put the plus there. There you go, done. So here, then, this question is about compounds containing ethane diurate ions. So a lot of people just fumble this horrendously because they just be like, you know what, bro, I gotta just go and work out moles and then hope for the best. Read the question. Like, this question is literally all about reading comprehension and just collecting the right pieces of information on what you care about, and that's it. Don't go in working out moles blindly. use a bit of common sense and just think. I promise, like, it doesn't hurt to use your brain. It's actually good for you, right? Because here in this exam report, it says only the best students got to the end. Many students just kind of worked moles out and that was it, and just kind of went for it. And it was like, right, what are you doing? Like, use the information in the question. This question's about compounds containing ethane diweight ions, right? So a white solid is a mixture of these two. So we have a white solid, which is made of Na2C2O4 and this H2C2O4.82H2O. I literally never do any of these questions without writing the key things because I just can't. So in this question, they said a volumetric flask contained 1.9 grams of this mixture of these two in 250 centimeters cubed. Fine. Two different titrations were run out with this then. So what they first did is in this first titration, they got 25 centimeters cubed of the mixture that they just made, right? They then added an excess of sulfuric acid in a conical flask, and then the flask and the contents were heated to 60 degrees and titrated with this much potassium manganate. When this much potassium manganate had been added, the solution had changed color. So then they've added, because that's what titrations are, you're using the concentration of a known thing to find the concentration or volume or whatever of another thing, right, that we don't know. They've added KMnO4 potassium manganate. We know the volume that they used was 26.5 centimeters cubed, and we know that its concentration is 0.02. Don't know anything about this mysterious mixture. Then what happened is it changed color. So then they gave you the equation for this reaction here, which is number 1. So I'm going to put number 1 next to this so I remember. Then it says in the second titration, which is a separate one, remember, titration 1, titration 2. It says in the second titration, they got 25 centimeters cubed of the solution. We'll go remember what the solution is. Every number in here, you should be able to know exactly what it is and where it came from. Remember that that's of the original mixture here, right? And then what they did is they titrated it with this much solution of sodium hydroxide using phenolphthalein. So they added NaOH, and its concentration is 0.100 moles per deciliter cubed. The indicator changed color as soon as the addition of this much was added. So we know its volume is going to be 10.45 centimeters cubed. Then it says the equation for this reaction is as follows, 2 here, right? Do this, because then you know exactly what's going on. One thing that drives me absolutely just, oh my God, right, is I'll do this with somebody when I'm explaining it, and then they just ignore like everything I've written here and then come back here and I'm like, what are you doing? Like they're like, oh, I've got to look at this equation. It's like, no, I wrote this here for a reason, dude. I don't write things for fun. I literally can't be bothered writing. Like, I don't want to do it, but I have to because this is so many words, right? So we've done this, we've established all the facts, and it says calculate the percentage of biomass of sodium ethane diweight in the white solid. So the objective is to find the percentage biomass of Na2C2O4. That's it, right? Now the rest seems pretty okay because we need to find out how much mass of solid is in here, and we've been given these two scenarios. First thing to do is, a lot of people just jump to working out moles of X and Y. I think the easiest solution is that this is H2C2O4, which is from here. That, working out the moles of this, would eventually be able to tell you how much is in that and knock it out. So if I look at titration 2 first, I know that, titration 2, I know that there's 2 OH minuses, which has come from here. So I know that however many moles of NaOH is going to be half as many of them. So if I work out the moles of NaOH, is going to be its concentration, 0.1 times the volume, 10.4 over 1,000, which gives you 1.045 times 10 to the minus 3. But I can see they're in a 2-to-1 ratio here, right? A 2-to-1 ratio of whatever's in this mixture, but the only thing in the mixture is this stuff reacting from that equation. So that means the moles of the H2C2O4 in 25 centimeters cubed, because it's in this sample, equals a half times 1.045 times 10 to the minus 3, which is going to be 5.225 times 10 to the minus 4 moles, right? Therefore, the moles of the H2C2O4 in the 250 centimeter cubed sample that we had initially is going to be this. Well, what's happened here? We had 25, we're going up to 250, so we're going to have to times the answer by 10, which is going to be 5.225 times 10 to the minus 4 moles. So then, in this white solid, I now know that the H2C2O4.2H2O, the moles of it is this answer that we just worked out, which is, times 10 to the minus 3, which is 5.225 times 10 to the minus 3 moles. Bingo, I've already worked out this. So whatever else is here is probably what's made of the Na2C2O4. So what I can do now is I can look at this titration here, number 1, with this equation, which is where everyone was like, oh, I'm going to work out the moles of manganate, and then I don't know what I'm going to do next. So if I look at titration 1, yes, you can work out the moles of manganate. Moles of MnO4 minus is going to be its concentration, 0.02 times 26.5 over 1,000, which gives us 5.3 times 10 to the minus 4. Now we can see that they're in a 5-to-2 ratio. So divide by 5 times by 2. So the moles of the, 2 to 5 ratio or whatever. So divide by 2 times by 5. Whoops. So here we can see that they're in a 2 to 5 ratio. So we need to find out the moles of C2O42 minus, moles of C2O42 minus, which could have come from either of these, which is why it was a problem, is going to be 5.3 times 10 to the minus 4. What we're doing is we're dividing it by 2 times it by 5. So what we can do is do times 5 over 2. If we do that, we get 1.325 times 10 to the minus 3 moles, but this is in 25 centimeters cubed. So in 250 centimeters cubed, is going to be this times 10. So 1.325 times 10 to the minus 2 moles. Now that means all of these C2O42 minuses from our little flowchart that came from him came from both of these. So that means that if I just move here, sorry, whoops, the moles of the Na2C2O4 must be this, the 1.325 times 10 to the minus 2, minus the one that we definitely know. We know that this many moles of whatever this mysterious mixture is came from here, right? So it's going to be minus the 5.225 times 10 to the minus 3. So 5.225 times 10 to the minus 3, which is going to be 8.025 times 10 to the minus 3. So now I know that the moles of this the Na2C2O4 in this mysterious white solid is 8.025 times 10 to the minus 3. Would you look at that? Because the question wants the percentage by mass of this in this 1.9 grams of solid. So that means our mass of Na2C2O4 is going to be its moles times the MR, which is going to be the moles, which we just worked out, of 8.025 times 10 to the minus 3, times the MR of Na2C2O4, which is 134. If you do that, you get 1.0754 grams. So then the percentage by mass is going to be 1.0754 divided by the total of this, which is 1.90, times by 100, and you get 56.6%. Done. The only way around this is by doing what I just did there. Reading through it, collecting the information you care about and need, assigning equations to each sentence where possible, or little flowchart, things like that, and the rest is quite all right. Because the problem is that people don't read any of this. They're like, I'm going to work out the moles, and then they just jump back and forth trying to look for bits. It's like, why are you suffering? Why are you making life harder? And why are you just doing it wrong? No formulas work in this, no routines work in this, that's the only way, soz. So ethane diurate ions react with aqueous ions in a ligand substitution reaction. Write an equation for this and suggest why the value of the enthalpy change is close to 0. So we're working with FeH2O 6 3+, and we're adding ethane diOH, which is C double bond O O minus O minus. It's an ethane dioic acid with the OH is gone, so it's just our minuses. So we're going to add 3 lots of C2O42 minus because it's a bidentate ligand, so it's going to have 3 of them around this one that can have 6 coordinate bonds. So it's going to be FeC2O4 3, and then we're going to factor in the charge. We've added 6 minuses to this, it's plus 3, so it's going to be 3 minus plus 6 H2O. The question says suggest why the enthalpy change of this reaction is close to 0. Enthalpy changes, remember, is exothermic and endothermic, bonds made, bonds broken. Now we're breaking 6 covalent coordinate bonds, and we're making 6 coordinate bonds. So that's exactly it. 6 coordinate bonds broken, 6 made. Same number of bonds broken and made. Enthalpy changes are all about heat energy within things and their transfers based on bonds breaking and bonds making. Endothermic bonds breaking, exothermic bonds making. So if you have the same bonds made and bonds broken, then it's going to be an enthalpy change of nearly 0. So it says draw the displayed formula of this complex formed in this reaction, indicate the value of this, and then state the type of isomerism. So here what we do is we start by drawing a central metal ion, you draw your dashes and your wedges and your bits and your barbs like that, and then you add it ligand by ligand. So start by doing the lone pairs for everything. So add the lone pairs and the exact atom that they belong to here like this, because it makes your life a lot easier. Then we're looking at C2O4, which is this, right? All you do is you just stick the other bits on like that. So then there's a C, double bond O, and then we've got a C to a C like this, double bond O, and then a C to, I hope you guys will do it a bit tidier than this, obviously, but double bond O, add the square brackets, 3 minus, there you go. Now this is an octahedral complex, so it's 90 degrees, and the type of isomerism it has is optical isomerism, because you can have a mirror image of this that's non-superimposable, meaning if, for example, if here's one of your hands, which looks a bit screwed up, don't worry, and here's your other one, you can't superimpose them. You can't put them on top of each other and make them match. So it's the same thing here. Whoops, optical isomerism. There you go. Generally, when you have 6 coordinate bonds and a bidentate ligand, you can have optical isomerism. Now it says ethane diurate ions are poisonous because they react with ions in the body. Ethane diurate ions are present in foods such as broccoli and spinach. So just one reason why people who do not eat these do not get suffer from poisoning. It's that the concentration is low in these foods. That's about it. A lot of people were saying that for some reason it's indigestible or it was firmly chelated to ions, so we're not free to be absorbed. It's literally just that, dude. Like, come on, man. It's told you in the question that it's poisonous and it will cause problems when you eat them. So the only reason it wouldn't cause problems is just not enough. Anyway, thank you very much. I hope that helped. Please like, share, and subscribe. You know the drill.